This is Earth. It's not really Earth, it's just a model of Earth, but how have we known for a long time the mass of Earth? What did we do? Put it on a scale and measure its weight? Weight and mass are different. So what do we do? Put it on a balance? You can't do that. And how have we known the mass of our sun for more than 200 years? And why did we only have approximate values for the mass of Venus and Mercury, but we did know all about Mars and Earth and Jupiter and Saturn and all that? Well, that's it. I mean, how do we know all this stuff? That's a pretty significant and important question. How did H.G. Wells know in around 1900 that when the Martians, the scary Martians who came down here and landed on Earth, would weigh 2.5 times as much? Now, we've known many of these values ever since 1800, when Henry Cavendish found the universal gravitational constant. He was looking for the density of Earth using this crazy contraption where he measured the gravitational force between two objects. Henry Cavendish did it back around 1800. He found the universal gravitational constant, which completed Newton's law of universal gravitation. Newton's law of universal gravitation said that there's a gravitational force that exists between any two objects in the universe. And that gravitational force is directly proportional to the product of the two masses and inversely proportional to the square of the distance between them. But he didn't have the gravitational constant that he needed to do all the calculations that we could do. How did we know the mass of Earth? How did we know the mass of the sun? Why have we known these things for more than 200 years? Well, let's learn physics. So let's imagine you're standing on Earth, and you can, while you are on Earth, drop things and find the gravitational acceleration. You can measure the weight of things versus the mass of things and calculate the gravitational field strength or the gravitational acceleration. And since we know that weight is gravitational force, that's its definition, and the equation for weight is W equals mg, and the equation for the gravitational force between any two objects is capital G, m divided by r squared. I'm using capital M for the mass of the planet, Earth in this case, the mass of the central object, and m is a little mass. R squared, the distance from the center of Earth to the outside, the center-to-center distance. And you can set those two equal to each other, so you have mg is equal to g, big M, little m over r squared. Little m's divide out, and you get this equation, gravitational field strength, the acceleration of gravity at the surface of a planet or at any position above that surface, is the universal gravitational constant, 6.67 times 10 to the negative 11, multiplied by the mass of the central object, divided by distance from the center squared. Now in our case, we want to find the mass of Earth. So we're looking for that mass of the central object, and we can calculate, measure the gravitational field strength, the gravitational acceleration, and the radius. We've known that for a long time, and Cavendish supplied us with the gravitational constant. Mass, looking for it. G, we can calculate it here, 9.8 newtons per kilogram or meters per second every second. The radius of Earth, 6.37 times 10 to the 6 meters. Take that and square it. Divided by the gravitational constant supplied by Cavendish, 6.67 times 10 to the negative 11 newton meters squared per kilogram squared. And you get 5.96 times 10 to the 24 kilograms, which according to that chart you see circled, yeah, it's the same thing. Here's our equation. If you're on the surface and you can find G, then you can calculate M. And if you know the M, then you can calculate the G at the surface. You're looking at something from far away, and you can see a satellite. You can see a moon going around a planet. Or you can see a planet going around the sun. Well, from that information, you can calculate the mass of the central object. Now, let's say you have the moon in orbit around Earth, or a planet in orbit around the sun, and you have all the values. You know that it takes 27.3 days for the moon to go around, and the mean radius of orbit, this isn't a circle, but we pretend it is for this case, 3.84 times 10 to the 8 meters. You know perfectly well that the moon is held in orbit by the gravitational force, and you know that the orbit is caused by a centripetal force. You can take those two equations and put them together. First, the gravitational force. It's It's the universal gravitational constant times the mass of the central object, the Earth, multiplied by the mass of the moon, divided by that radius of orbit, squared. And then the centripetal force is, of course, the mass of the revolving thing, the moon, mass of the moon, multiplied by the speed of the moon squared, tangential speed, divided by that same radius. So you take those two, you set them equal to each other, because the gravitational force is the centripetal force, and you get big G, big M, mass of central object, mass of moon, over r squared is equal to mass of moon Vt squared over r. Now stuff cancels. Mass of the moon, the mass of the satellite divides out. One of the radius of orbits divides out on both sides, and you end up with universal gravitational constant times mass of central object, big M, divided by the radius of orbit is equal to the tangential speed of the satellite squared. Square root of both sides, you get the satellite speed equation. Vt is equal to the square root of the quantity gm over r. For the moon-Earth system, using the moon to find the mass of Earth, solving for m, move the r to the numerator, the capital G to the denominator. You get r Vt squared divided by g. Then, tangential speed is just circumference, right? So it's circumference, distance around the circle, divided by time, so it's circumference 2 pi r squared divided by t squared. T is the orbital period. And 2 pi r over t squared, well, I can reduce that to 2 squared, pi squared, r squared times r divided by t, and then absorb that g into the denominator. So you get 4 pi squared r cubed over t squared g. Complicated, I know. 4 pi squared times r cubed divided by 27.3 days squared, 86,400 seconds in a day squared, because it's t squared, and 6.67 times 10 to the negative 11. Put that all in the calculator. And 6.02 times 10 to the 24 kilograms. Same answer as before. Or you take 4 pi squared times 384 times 10 to the 6 cubed, raised to the power of 3, divided by 27.3 squared, divided by 86,400 seconds squared, divided by 6.67 e negative 11, you get the answer. 6.02 times 10 to the 24 kilograms. That's what I prefer, because I don't like parentheses, and I just, denominators are difficult, so I just divide by each piece in the denominator. So how did we know? Well, if you happen to be standing on a planet or standing on the moon, and you can calculate the gravitational acceleration or the gravitational field strength, then using the equations we have, you can find the mass of this central object. Or, like moon around Earth, you can find the mass of the central object if it has a satellite. Or the mass of the central object if it has a satellite. The reason we couldn't find exactly the mass of Mercury, the mass of Venus, is because they didn't have satellites. They don't have moons. And the moon, we had a pretty good approximation of the mass of the moon, but it doesn't have any natural satellites around it, so we didn't know gravitational field strength until we went there to really find it. There are good ways to calculate it, good estimates using the law of gravitation, but you don't know exactly until you really go there and get the values. 200 years ago, when Cavendish found the universal gravitational constant, we were then able to calculate the mass of Earth and the mass of the Sun and the mass of Jupiter. And here are the equations we use. Weight is the force of gravity, so little g, capital G m over r squared, where big M is the mass of the central object. And on the right, we have the satellite speed, Vt, and the big M is the mass of the central object. And H.G. Wells, back in the late 1800s, wrote The War of the Worlds. It's turned into a couple of movies, but it's good. A sudden chill came over me. There was a loud shriek from a woman behind. I half turned, keeping my eyes fixed on the cylinder still, from which other tentacles were now projecting, and began pushing my way back from the edge of the pit. A big, grayish, rounded bulk, the size perhaps of a bear, was rising slowly and painfully out of the cylinder. As it bulged up and caught the light, it glistened like wet leather. 2 large, dark-colored eyes were regarding me steadfastly. The mass that framed them, the head of the thing, it was rounded and had, one might say, a face. There was a mouth under the eyes, the lipless brim of which quivered and panted and dripped saliva. The whole creature heaved and pulsated convulsively. A lank tentacular appendage gripped the edge of the cylinder. Another swayed in the air. Those who have never seen a living Martian can scarcely imagine the strange horror of its appearance. The peculiar V-shaped mouth with its pointed upper lip, the absence of brow ridges, the absence of a chin beneath a wedge-like lower lip, the incessant quivering of this mouth, the gorgon groups of tentacles, the tumultuous breathing of the lungs in the strange atmosphere, the evident heaviness and painfulness of the movement due to the greater gravitational energy of the Earth. Above all, the extraordinary intensity of the immense eyes were at once vital, intense, inhuman, crippled, and monstrous. There was something fungoid in the oily brown skin, something in the clumsy deliberation of the tedious movements unspeakably nasty. Even at this first encounter, this first glimpse, I was overcome with disgust and dread. I began to comfort her and myself by repeating all that Ogilvy had told me of the impossibility of the Martians establishing themselves on the Earth. In particular, I laid stress on the gravitational difficulty. On the surface of the Earth, the force of gravity is 3 times what it is on the surface of Mars. A Martian, therefore, would weigh 3 times more than on Mars, albeit his muscular strength would be the same. His own body would be a cope of lead to him. That, indeed, was the general opinion. Both the Times and the Daily Telegraph, for instance, insisted on it the next morning, and both overlooked, just as I did, 2 obvious modifying influences. The atmosphere of the Earth, we now know, contains far more oxygen, or far less argon, whichever way one likes to put it, than does Mars. The invigorating influences of this excess of oxygen upon the Martians indisputably did much to counterbalance the increased weight of their bodies. And, in the second place, we all overlooked the fact that such mechanical intelligence as the Martians possessed was quite able to dispense with muscular exertion at a pinch. Thanks for watching Learn Physics. And thanks for that thumbs up, too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.